Welcome back to the deep dive. Today, we're zooming in on something you probably never think about, but it's literally the skeleton of modern industry. We're talking about modular aluminum framing systems.
Yeah, this is the stuff holding up everything. Multi-million-dollar automation lines, robotic cells, precision equipment in aerospace, pharmaceuticals. It's everywhere.
And if you're not an engineer, it just looks like a metal frame. But here's the problem we're going to dig into, and it's a huge one. The success or failure of that multi-million-dollar machine, it all comes down to the integrity of its tiniest connections.
That's it. If the frame shakes, even microscopically, that super precise robot or sensor mounted on it is basically useless.
So this is where the status quo comes in. For decades, the standard has been what's called a T-slot aluminum frame.
Right. And it's popular, it's fast, it's modular. But the engineering behind it relies almost completely on what we call friction-based connections.
Friction.
Yeah.
Okay.
So it's okay for maybe some shelves or a very light static workbench. But for the demanding stuff, anything with vibration, dynamic loads, or where you need micron-level precision friction it's a fundamentally flawed approach.
So that's our mission for this deep dive. We're going to unpack the technical reasons why that old standard is so unstable. And then we'll explore an alternative, angle lock, which completely rejects friction. They're claiming to be 10 times stronger by creating a genuine mechanically locked joint.
A joint that actually gets tighter under stress.
Okay, let's unpack this. For someone without a background in structural mechanics, what exactly makes a friction connection so unreliable the second you introduce, a motor or any kind of movement?
Well, it really comes down to basic physics and geometry. A traditional T-slot needs you to tighten a fastener with extremely high torque. A huge amount of force.
Right, you're just crushing it together.
You're crushing it. That torque creates a massive clamping force between the two aluminum profiles, and that force is what generates frictional resistance to movement.
So you're just betting on friction to do all the work.
Exactly. But here's the kicker, the real flaw. The connection is based on a single plane friction model. If you look at how the bolt and the little T-nut sit in the slot, that single point of contact creates natural pivot points.
Ah, okay. So it has a built-in desire to twist or move.
A built-in weak spot. You're just relying on brute force, the bolt crushing those two surfaces together to keep the joint from moving.
So if that clamping force is the only thing holding it together, and you've got these pivot points, what does that actually look like on the factory floor? What are the real-world consequences?
You see four really critical and predictable failures. The first one, and honestly the most costly, is just loosening.
It just comes apart over time.
Yep. Under dynamic loads, constant vibration, think of a motor running anywhere nearby. That friction gradually breaks down. The joint slips, it loosens, and then it needs constant maintenance, constant retightening.
And that means downtime. I've heard stories about maintenance guys whose whole job is just walking the line with a torque wrench.
That hidden labor cost is an absolute killer for efficiency. Then the second problem is what we call the oversizing requirement.
Meaning you have to build bigger than you should.
Exactly. Engineers know these connections are weak. So to compensate, they have to use aluminum profiles that are far larger and heavier than the actual beam needs to be for the load. They're over-engineering the whole structure just to make up for a weak joint.
So you're using a beam that could hold up a car just to make sure the joint doesn't fail, holding up a tiny sensor.
That's a perfect analogy. Third, you have precision failure. That little bit of give, that microscopic movement that the pivot point allows, means you can't hit your precision goals. You just can't get micron-level accuracy if your foundation is constantly shifting.
It's impossible.
And finally, there's a really self-defeating flaw in the design. To get that friction, you have to apply that extreme torque we talked about. But when you crush soft aluminum that hard, you actually distort the profile.
You're damaging the part.
You're bending it beyond its original manufacturing tolerances. It's like over-tightening a screw in wood until the wood itself starts to split. You are literally compromising the precision of the material just to make a weak connection.
Wow. That really is the ultimate catch-22. You damage the structure while trying to stabilize it. So it sounds like T-slot just has this built-in, predictable failure mode.
It absolutely does.
All right, so this is where it gets really interesting for me, moving into the solution. If friction systems are designed to loosen, how does angle lock completely flip that? How do you make a connection that actually tightens under stress?
They do it by completely abandoning the idea of friction. They switch to what's called multiplane mechanical locking. They use specialized angled fasteners and a unique geometry to physically eliminate those pivot points.
So you're not fighting movement, you're physically blocking it.
You're blocking it.
Yeah.
Creates what they call a bonded connection. And the core idea here is using a very specific high-strength bolt that you tighten just to the point where it begins to stretch.
It stretches, a steel bolt.
It stretches elastically. And that stretched bolt acts like a really powerful spring, constantly pulling the components inward, maintaining that perfect alignment.
So if vibration tries to shake the joint apart, the spring just pulls it right back together.
Precisely. The dynamic loads, the vibration, they actually help maintain or even increase the connection's integrity. It becomes a self-maintaining structure. It's designed for zero loosening.
That certainty is everything. Okay, let's get into the mechanics. This is the detail that backs up that 10 times stronger claim. How do these 5 sequential planes of anchoring work to eliminate all possible movement?
Absolutely. So don't think of it like tightening one screw. Think of it more like setting a combination lock where each step prevents movement on a different axis.
Okay.
So planes 1 and 2 are the foundation. A special nut anchors deep inside the V-shaped channel of the profile. This sets the initial anchor point, stops it from sliding or rotating right at the start.
Got it.
Then comes plane 3, the rotational lock. As you start to tighten, that nut rotates up and physically locks into the opposite wall of the profile. This creates a mechanical 3-point anchor.
So it's not friction, it's a physical block. That's what eliminates the pivot point.
You got it. You have fundamentally eliminated the potential for that profile to twist or pivot away. Then you move to plane 4, which is precision alignment. An upper bracket slides into place before you apply the final force.
So you're guaranteeing it's perfectly aligned before you lock it down.
Exactly. It establishes that perfect geometric relationship. And then finally, you get to plane 5, the spring tension lock. The steel bolt is tightened to a very precise torque, about 180 inch-pounds.
Which is enough to stretch the steel.
But not enough to distort the aluminum. That's the key. That controlled stretch completes the full mechanical lock. It guarantees that lifelong integrity.
It sounds revolutionary, but let's be realistic. If it's 10 times stronger and never needs maintenance, what's the catch? Is the specialized hardware and this complex process making it way more expensive than T-slot?
That's a fair question. And yes, the initial component cost for the specialized hardware is higher than basic T-slot parts, but the trade-off comes in long-term savings and in optimized design.
How so?
Because the joints are so incredibly rigid, engineers can often use smaller, lighter profiles than they'd need for a T-slot system. So that offsets some of the material cost right away. But when you factor in zero maintenance and guaranteed uptime, the total cost of ownership is dramatically lower.
So let's talk about those hard performance numbers. What does this new mechanism actually deliver?
The jump is, it's staggering. We're talking about joint strength that is 10 times stronger than traditional friction systems. And even more importantly, the rigidity is comparable to welded steel joints.
Welded steel. So you're getting the strength of welding, but you can still take it apart and reconfigure it.
That's the holy grail, right?
Yeah.
All the structural integrity of welded steel, but with the total flexibility of a modular aluminum system.
The materials must play a big role in that too.
Oh, for sure. This isn't just any aluminum. The extrusions are 6105 T5 architectural grade. That means it's designed for high strength and stability. It's about 1/3 the weight of steel, but gives you double the strength-to-weight ratio.
And we talked about the zero maintenance benefit. I've got to assume this rigidity also makes it faster to build with.
50% faster on average. The brackets are self-aligning. The kits can be pre-assembled. You're not spending all your time fighting with T-nuts trying to get things square while you're torquing them down. It just snaps into place before you apply the lock.
Now, this technical certainty, this is what lets engineers really push the envelope. With T-slot, it sounds like they were always over-designing out of fear.
Out of necessity, yeah.
But with this, you're saying they can use tools like finite element analysis to model everything perfectly?
And for listeners who might not have that background, let's quickly touch on FEA. It's basically a digital stress test for engineers.
A simulation.
Exactly. You build a complex 3D model, you apply virtual forces, vibration, weight, torque, and the software predicts exactly where the structure will bend or twist or fail.
So if your model is accurate, you know exactly how much material you need. No more guesswork.
Right. And T-slot is a nightmare to model in FEA because its friction is unpredictable. It degrades. So engineers have to be hugely conservative, which means heavy, expensive structures. But Angle-Lock's bonded joints behave predictably every single time. So the FEA models are accurate.
which means they can optimize the design, use less material, and save weight and cost.
with total confidence.
Okay, so let's see where the certainty is paying off in the real world. What kind of data proves these connections actually hold up under pressure?
The evidence is coming out of the most demanding fields. So take robotics. They're maintaining plus or minus 5 microns, repeatable positioning accuracy.
5 microns. Put that in perspective for me.
A human hair is about 100 microns in diameter. So we're talking about 1/20th of that. T-slot systems they can't hold that kind of tolerance over time.
Wow. Okay. What else?
In high-speed material handling, things like docking carts, they're getting plus or minus 0.03 of an inch repeatable accuracy. And the data shows the tiny bit of variance they see is actually from the cart wheels and the floor. The joint itself is showing 0 variance.
Rock solid. And what about those extreme vibration tests? Like bolting a frame directly to a giant industrial compressor.
0 loosening, even under continuous high-frequency vibration. And that's critical for things like CNC machine enclosures, where traditional fasteners would be a constant maintenance headache.
This level of stability must open the door to some really high-stakes industries where, failure just isn't an option.
Absolutely. Think about clean rooms. The material and the finish are non-particle shedding. They're chemically resistant, easy to clean. They're certified up to ISO Class 1. That's essential for making semiconductors, microelectronics, pharmaceuticals.
And I imagine aerospace and defense would be all over this.
They need that extreme vibration resistance for things like avionics test stands or satellite assembly fixtures. And they need frames they can reconfigure as programs change without losing that micron-level precision.
And of course, robotics and automation, the heart of modern manufacturing.
They need to handle the punishing high-frequency vibrations of automated processes and, provide that perfectly stable mount for vision systems and lasers. This system is really built for Industry 4.0.
So the long-term benefit is that the structure you build on day 1 is the exact same structure you have on day 1,000. No structural drift.
It maintains its original characteristics indefinitely. For capital equipment, for safety-critical applications, that kind of predictability is priceless.
So, wrapping this all up, what's the core takeaway here for our listeners, whether you're an engineer optimizing a design or just someone trying to understand the next step in industrial tech?
The core distinction is this. Angle lock isn't just a better version of T-slot. It's a fundamental upgrade over the predictable failures of any friction-based system. It delivers the structural integrity of welded steel, but it keeps the single greatest advantage of aluminum framing.
Infinite flexibility.
Infinite flexibility. You can take it apart, reconfigure it, rebuild it 100 times, and you never weaken the integrity of the joints.
It's the difference between building a maintenance liability and creating a permanent, flexible foundation.
The real innovation is that geometry, but the result is guaranteed engineering certainty.
So here's the final thought for you to take away. Given that the system lets engineers design lighter, fully optimized structures that require 0 maintenance over their entire lifetime, just consider the massive cumulative impact. Think of the materials saved, the weight reduced, and maybe most importantly, the operational downtime eliminated. If this mechanical locking approach became the new standard across all heavy industrial automation, that shift from friction-based instability to bonded mechanical certainty, that could really define the next era of industrial design.